In this lecture, we will discuss some issues with regards to the kernel stack and priorities in Linux. So the first question that we would like to ask is, where does a process keep its information after a context switch, and who works for the process or does work on behalf of the user process once it is in kernel mode? So is there like another kernel thread which is an avatar of the process that runs in kernel mode, or what happens? So this is a complex mechanism. We'll get many chances to look at this over and over again. At the moment, it simply suffices to say that there is a user thread. So we're looking at the user to kernel transition. There's a user thread. Then there is a transition into kernel mode where there is another kernel thread. It's not a separate thread. So what actually happens is that the same user thread kind of transitions into kernel mode and transitions back. But this is a complex concept. We don't want to delve a lot of time. We don't want to delve into this or spend a lot of time discussing this. But it simply suffices to say that is the kernel thread that does the job of storing the context in a memory location and also doing the work on behalf of the user thread, which is servicing the system call. So it has a dedicated stack because a stack is always required to store the local variables. So this is why every user process is associated again with a kernel thread which does the work for the process in kernel mode, and it has its private stack. And given that all the processes in the kernel, right, all kernel threads share the virtual address space, so the stack here is not really private in that sense. But again, a stack has to be private because multiple threads cannot modify it. So what actually happens is that there are a lot of restrictions on this stack such that every thread gets its private stack and it is guaranteed that no other thread can write into it. So effectively, it is a private region, even though all the kernel threads share the same virtual address space and consequently the same page table also. So the way that this works, right? So we have already seen like half of the working, which is that the user thread transitions into kernel mode because it makes little sense to actually spawn a new kernel thread to do the job of the user thread or spawn it at the beginning and somehow keep it dormant. Those are all bad ideas. So a better idea, of course, is to let the same thread do the job. But of course, it needs to be in a new kernel avatar and definitely use a different stack, because whatever happened in kernel mode, you don't want that to be accessible in user mode. So the moment we have a different stack, an issue can always arise where someone can say that two different kernel threads ended up overwriting to each other's stack, the classic overlap problem. But this will not happen. The reason is that the stack size in the kernel is limited to 8 KB. So we place a hard limit. So what happens is that let's say for one kernel thread, the stack is over here. For another kernel thread, the stack is over here. So the stacks, these 8 KBs are laid out in such a way in memory that there will never be any overlap. Hence, in practice, regardless of the fact that there is one virtual address space, every kernel thread has its private stack and they contain useful data as long as the thread is alive and also if the thread is in the zombie state. So system calls are one way of transitioning from user to the kernel mode, but the other mode is interrupts, where a regular program is running and a hardware interrupt arrives. So what happens in that case is that there is a need to again run an interrupt thread, which similar to the earlier pattern could be the same user thread that has simply transitioned to kernel mode. In theory, a separate interrupt thread can also be started and run, right? Something which has a very high priority. But we would not like to use the same kernel stack. I mean, assuming a user mode thread is transitioning to the interrupt mode, the kernel mode, we would not like to use the mechanism that was used here. The reason being that in general the interrupt state is of a highly sensitive and secure nature. It is not the processor's data that is being processed. This is why it's a good idea to have a separate memory region. That is one. Sometimes we may need more than 8 kilobytes. That is the second reason. The third reason is that sometimes when an interrupt handler is being run, another interrupt arrives, so there's a need to store the current context and then start the second interrupt handler, which would again need one more stack. So that is why typically the kernel stack is not used, but there is a separate interrupt stack for interrupt handlers. So what we have seen is that when an interrupt handler is running, it's possible another hardware interrupt comes, so another interrupt handler runs. Right, the first one is paused. Another high priority interrupt comes, such as a non-maskable interrupt, which cannot be ignored. Then another interrupt handler runs. So that is why we need several stacks, because the moment an interrupt handler has to be spawned, it can take a free stack and it can simply start running. So what Linux does is that with every CPU, it maintains 7 dedicated interrupt stacks. The moment an interrupt handler needs to run, it picks one of the stacks that is available, uses that, and it starts to run. If it finishes, well and good, right? So all the temporary data in the stack can be cleared up. If it does not finish, before finishing another interrupt arrives, then there is an handler to handler context switch, and the new handler again picks up a free stack and it starts to execute. So a 7-level interrupt nesting is supported. This is enough in practice, so we do not need a higher level of interrupt nesting. This is enough, so more than that is not needed. And we do not expect that many interrupts to come in parallel unless, of course, someone is trying to hack the system, which is why it's enough for every CPU to have 7 interrupt stacks. And the moment an interrupt handler needs to run, it just picks up a stack and starts to run. So given the fact that we have looked at the kernel stack, the limitations on the kernel stack, and the fact that the kernel stack is not preferred while running an interrupt handler, but a separate interrupt stack is used. Furthermore, while running a handler, it is possible that an interrupt can come in the middle, so there would be a need to store the state and start a new handler, especially if it's a higher priority interrupt or a non-maskable interrupt. We need multiple such interrupt stacks, but again, there has to be a limit to everything. So in this case, the limit is set to 7, which is much more than what is required in practice. So we will next try to answer the question that given this specific structure of the stack, I would like to find a pointer to the task struct of the current process, and that too very, very quickly. This needs to be a very efficient process because this same operation is invoked hundreds of times, thousands of times, and even an extra instruction is actually too much.
So we will discuss the structure of the stack in older kernels, and this method is not used right now, but it will give us some idea as to what is the role of efficiency in designing the kernel and how in many cases only 1 or 2 instructions have been saved, but that does turn out to be a big savings, mainly because if let's say one operation is invoked hundreds of times extremely frequently, then even a 20% savings may translate to a 2 or 3% savings in the overall speed up of a program, which is quite large. So in general, operating systems are not responsible for a lot of speed up, but wherever it is possible, that should be done. So what we have discussed is that a stack frame has 8 kilobytes, which is like this. There are many different options. You can have a downward growing stack, upward growing stack. So let us consider the classical downward growing stack. So in this case, this would be where the stack is starting, and then an 8 kilobyte zone or a 2-page zone is allocated to the current process, current kernel process. But the fun part is that all of it is not usable. The thread info structure is stored at the bottom. So the maximum point that the stack can actually go to is actually this point. It cannot cross beyond that, because beyond that it will overwrite thread info, which is not allowed. So we deliberately keep thread info at the bottom of this region. An advantage of doing this is like this. So of course the bottom of this region is aligned to, so it's some multiple of n into 8 kb. So it's aligned to an 8 kilobyte boundary. All right. So the main aim is that if, let's say, I have any address within the stack, I should be, let's say I have this address within the stack, which could be the address of my current stack pointer, or it could be the address of a variable that is stored on the stack. I need to quickly get here, right? I need to quickly get here to this 8 kb boundary. So if you think about it, let me give you a similar problem. You will see how easy it is. Let us say that I have any decimal number and I would like to find the largest multiple of 100 that is still less than the number. So that is actually very easy. Say the number is 17,567 and I want to find the largest multiple of 100 that is less than the number. All that I do is I replace these two with 00. That is all that I need to do. See, if I can do this in decimal, I can do this in binary also. If I want to find the largest multiple of 4 that is smaller than a number, then 4 is nothing but 100 in binary. So all that I need to do is I need to take the binary string, one second, whatever it is, I need to take it So all that I have to do is that I have to convert these two to 00 and it will become a multiple of 4. So what you see over here is basically that if I want to align it to an 8 kb boundary, 8 kb is nothing but 2 raised to power 13, which is 8192. Alright, so that is 8 kb. So all that I need to do is, so 4 is 2 raised to power 2. So I'm zeroing out the two LSB bits. In this case, I take an address and I zero out the 13 bits. I just convert them to zeros. That is all that I need to do. So what I, in a sense, need to do here is that I take any address and I AND it with a number, which is 11111 and then 000, 13 zeros. That's all that I need to do. And this is easily doable in the x86 ISA. And within one instruction, I can reach this point. All right. So that is the first brilliant aspect of this design. The second brilliant aspect of this design is that recall that thread info is a low-level data structure, which means it is hardware aware. When I'm doing the structure definition of thread info, what I do is that I declare thread info. The first variable, okay, the very first variable is a task struct star, okay, something. The very first variable is a pointer to a task struct. This will ensure, so it all depends on how it is laid out. So if the very first variable is laid out over here, then basically at this base location, which is accessible with a current macro, the base location will store the pointer to the task struct, which essentially means that the next, let's say the pointer is 8 bytes, the next 8 bytes will be a pointer to the task struct. So this approach requires two instructions. One is the AND instruction. The second is a load instruction at this location to find the pointer to the task struct. Once that is done, I have a pointer to the current task that is executing, and then I can do whatever I want to do with it. but broadly speaking, this is the approach where I have a mathematical operation which takes me to the starting point immediately, and then I lay out my fields in such a way that task struct is the first field that is there where it becomes quickly accessible. Right, so there are two tricks. One, the first is a mathematical, second is a data laying out trick. So this approach, of course, is not used now. We will discuss a faster approach, which instead of two instructions requires one instruction. So which is why the thread info structure, it's still there, but it has become much smaller because its original use is not there anymore. Its original use was this, to be a small struct. You can't store the entire task struct here because the entire task struct is a large structure and it will eat up a fair amount of that 8 kilobytes. That is why storing all of it here was precluded. Instead, you need to store a pointer which requires these two smart little things that you need to do. So we will see there are many such instances in the kernel code where the way that a structure is laid out in memory actually becomes very important, right? So any low-level programmer has to be aware of these details. So now we go here and see what happens in the current kernel. So in the current kernel, what happens is you have a current macro. So the nice thing with the current macro is everybody uses it and they don't really care how it is implemented. It's like a preprocessor function, right? In a function, you just use it. You don't care how it's implemented. But a macro, of course, does more, right? So that we know, that we have discussed. So what we basically do is that we declare a per CPU variable, and this is a macro, which basically defines current task as a pointer to the current task structure. Furthermore, we define another macro get current. So mind you, this is, this is an inline function. An inline function is effectively a macro in the sense what it does is that you don't have a function call and a function return. And in an inline function, the entire function is expanded and copy pasted right there. So you don't like go anywhere. So you don't have that additional overhead that a function has. What are the overheads that a function call has? Well, storing the registers, restoring the registers, function call, function return, creating the stack, none of this is there. So in a certain sense, it's a programmer's way of creating a macro, but you still want the elegance of calling a function. All right. So what you do is that you essentially read the value of the GS segment register, right? And then that is put into current task, right? We will see how. And so basically, the thing is that so current and get current are the same. So the moment I call current in the kernel, so it will actually call the get current inline function, and the inline function will read from the current CPU the value of a segment register, and that segment register has a pointer to the current task. So even though it may appear that there are a chain of functions and macros, when the compiler actually compiles and generates the code, right, it will translate to a single instruction, which is nothing but get the pointer to the current task and store it in a global variable. All right. So the CPU reads table macro reads this task struct pointer from a separate per CPU region, right? And where is that per CPU region that is storing the task struct pointer? It is pointed to by the GS segment register, where there is a region, and from the start of the region, it is known where the task struct pointer is there. So in a single instruction, you can do a single load from the GS segment register and get the pointer. Instead of two operations, you need only a single operation, which is why the earlier mechanism has been superseded by the current mechanism, which is this. It does appear slightly complex when you read it because you see, number one, you see a current macro, which resolves to the get current inline function, which is this, which again resolves to another function call, right? Or macro call. So when something is called in C, you don't know whether it's a function or a macro, right? Because both of them while calling look the same. But anyway, you go there, and finally that will resolve to basically loading something from a memory address and putting it in this, broadly speaking, right? That is what is happening. So now that we have seen the fact that the current task struct is something that we need it a lot, and we need it very frequently, and we need it very quickly, which is why we invested so much of effort in getting the current task struct in a single instruction. So let us look at some of the options that could have been available to us and why they were not chosen. So clearly, this mechanism was chosen over other options. What were the other options? The other option was that I dedicate a general purpose register for storing the current task struct. The problem there is we have a limited number of general purpose registers, so we will lose by one. Also, the other thing is allocating general purpose registers, managing them is completely the compiler's prerogative. So it is hard to force the compiler to say that you always keep this in a register. Even the register keyword in C is suggestive. You are telling the compiler that this is high priority data, kindly keep it in a register, but you can't order the compiler. The other is store it in a global variable, but again, first is it has to be CPU specific, so which means you'll have to store it in some kind of an array, right? If there are, let's say, 10 CPUs, you'll have an array with 10 elements where each element points to a task struct. When you're writing a high level program, this may sound to be a reasonable idea, but when you actually translate it into instructions and you count, you will see there are a lot of instructions. Find the base of that array, then find then load. So that does involve extra work. All right. So other is store a pointer to it at the bottom of the stack. The way we did that required predominantly two instructions, which we are making one here. The second is use a model specific register, which is like a privilege register within the CPU. Technically, it's not a bad idea, but the fact is that if we have 32 CPUs, you need 32 such registers. And that many privilege registers are not there for this purpose. Also, privilege registers are not really kind of a universal standard, right? So it's not like a general purpose register that all processors in the family will always have those registers. They tend to change. So not a very portable solution. So the local storage area in the CPU, which is addressable from the GS segment register, was found to be a reasonable solution. All right. So the entire game is done like this, that the GS segment register stores a pointer to a per CPU region, and the segment register is a property of the CPU. Every CPU has a different segment register. So this segment register simply points to a region there where not only the task struct but a bunch of variables which are relevant only to the CPU, they are stored there. All right. So we will see that this is kind of like my private, hyper accessible, quickly accessible storage area, and I am making good use of my segment registers for this purpose, right? Because as I discussed in x86-64, the only segment registers that are used are FS and GS, right? The rest are not used, and as you can see, we are doing good. We are making good use of them. In fact, Linux has a macro defined per CPU, which allows you to create per CPU regions and store their addresses in segment registers. All right. So the question was that, why is a segment register a segment register? Well, that follows from the segmented view of x86 memory, where we sort of virtualize the virtual address, have a data segment, code segment, and so on, which is something that we discussed, that the CPU generates a logical address. The logical address is added with the contents of the segment register. The output is a linear address. The linear address is what we have sort of been thinking as a virtual address up till now, because this is the one that undergoes virtual to physical translation. So this is broadly the thing. And depending upon the access, in many cases, the CPU can automatically figure out which segment you are using. Otherwise, there is a way to explicitly specify the segment you want in the format of a memory operand itself. For example, you can do %fs 4 %esp. This basically means the logical address is 4 esp plus 4, and the segment is fs. So there are some things we need to keep and bear in mind here. They are not very obvious when you are writing application code, but the moment you get into a little bit of high performance code where that 5%, 10, 20, even 25% matters, you have to ensure that a 64-byte line starting at a multiple of 64 bytes is never shared across processors. It is never the case that I have a 64-byte chunk of memory where kind of core 0 is accessing this part and core 1 is accessing this part. Because 64 bytes is an atomic unit in the memory system, typically 64 or 128 depending on the system. So if I want to write even 1 byte, I need this entire chunk, entire block. And if I want to write 1 byte and I'm core 1, I need this entire block. So what will happen is that the cache line will bounce a lot even though the addresses are non-overlapping. This is known as fault sharing. So to avoid fault sharing misses and cache lines bouncing between cores, we have to ensure that alignment constraints, alignment rules are respected. Alright. So that is why when these regions are created, you have to be very disciplined and align them to 64 or 128 byte boundaries, as may be the case. So now we have discussed the kernel stack in some level of detail. So hopefully we have appreciated that if you are writing serious code, then small interactions matter because they reduce the performance substantially. So that is why you need to worry about instructions. So this solution of keeping it at the end of the stack was a good idea because you could quickly go here, and from there here you could go here. But a better idea was you directly use the segment register that you have to go there. Alright. So this is broadly speaking what we have learned in this part, how to get quick access to your information. So the kernel stack is pretty much the state that the kernel thread maintains. The kernel thread is kind of the mirror thread, because if I am a user thread, the moment I go to the OS, someone needs to do my job. So the kernel thread does the job. For the time being, you assume that they are separate entities. The user thread and its partner kernel thread are separate entities. In a later chapter, we will sort of tell you that they are actually the same entity. It is just that when I go to the kernel, I become a different person. I wear a different dress. It's like Jekyll and Hyde. Alright? That when I'm in the user mode, I operate in a certain way. When I'm in the kernel mode, I behave in a certain way. Right? So we will discuss this. So there are complexities here. But let's for the time being keep matters simple. So the question is that the kernel thread needs its work area, which is the stack. Also, you always want access to your task struct, and there is a quick way of getting access to it. All right, because task struct is like that one master data structure which everybody points to. Okay, so now you have access to your task struct, your kernel thread starts executing, it does its job. So you have a bunch of threads. You have user threads, you have kernel threads, you have ultra high priority threads that are processing interrupts, and the interrupt threads are using a separate stack, a CPU specific stack. So the question is that how do they run? Let's say I have 100 threads, how are they actually scheduled? So we need to understand this notion of process priorities. So clearly different processes have different priorities, and the priority range in Linux is, or all other Unix like operating systems, is from 0 to 139. But it is sort of slightly complicated and tricky. The real-time priorities are from 0 to 99. Where a real-time process is something that is associated with a deadline, which means that the computation needs to finish by a certain point, whatever you are doing. So real time would be something like video processing. If it is a 60 hertz frame rate, then you have 16.66 milliseconds for generating each frame. This means whatever you do, the computation has to finish in 16.66 milliseconds. This is a real time task. Of course, this is not a hard real time task like the one running on a rocket, because in case you miss a frame, you will see a little bit of a jitter. In most cases, you will not be able to make out. But what is called a hard real-time system is the one that you have on a rocket or a missile. So the real-time process priorities are from 0 to 99. User priorities are from 100 to 139. All right, but they don't monotonically increase. It's kind of slightly strange. Let's look at it. For real-time processes, higher the value. So I have this graph here. So we will actually go back. Sorry, this should be a TU. So so what it says is that for real-time processes, higher the number, higher the priority. So 0 is the least priority real-time process and 99 is the highest priority real-time process. But for user processes, higher the number, lower the priority, which means that 100, a user process will always have a lower priority than a real-time process. So 100 actually has lower actual priority than 0. And then as you go towards 139, it reduces. So this is what your graph looks like, right? Where the plot looks like, where the priority value or the number is the x-axis and the actual priority is the y-axis. In the case of real time, as you increase, your actual priority increases, which means the highest priority process in the full system is the one with priority 99, right? That has the highest priority, and he has strongly advised not to run anything with a priority more than 60 or 70 because the entire system will become unstable and crash, right? So people are advised not to tinker with real-time priorities unless they want to crash the system. Even the kernel itself runs a lot of its own work in priority 50, right? So, but again, Linux was made to run on all kinds of systems, including missiles and rockets and drones and everything. So they may need these ultra high priority jobs, but then you will have to design the system very carefully. All right, otherwise things may crash because then only this will be running, other work will not be happening. All right. So given the fact that we have seen this diagram, which again arises because of this for historical reasons. So let us look at this once again. For real-time processes, higher the value, higher the actual priority. For regular processes, lower the value, right, higher is the actual priority. It is reverse. So the question is that if I run a regular program, just I open a command line and open VI or Emacs or something, it runs at a priority of 120. Now, should I give the user the power, a regular user the power to increase the actual priority? That does not seem reasonable. Otherwise, everybody will do that. That is why the reverse power is being given. That I can actually reduce my priority in the sense if I am not doing something that is important, I act like a good citizen and I reduce my priority such that my friend who is running his homework gets more priority. So this command, as the name would suggest, is called nice. All right. So what I can do is I can do nice minus n, let's say 10. Right. And then I either give the command or the process ID or whatever. And then what will happen is the priority will become 130. All right. So if I'm doing a fresh command, I do a fresh command. And then I say that you run this priority with the run this command with the priority 130. All right, 130's priority is actually low. I'm being nice. All right, that's the name of the name of the command line utility is nice. Right? I can be nice. I can reduce my priority. But if I am the super user, mind you, is not the kernel. Super user is just the administrator of the system who has more power over other users, but is still a user. So can make changes to the file system, install updates, create users, and so on. The super user can provide a negative priority value. Okay, so super user can convert, let's say, 120 to 105. Only the super user has been given that power, but a regular job cannot be made a real-time job. I mean, not via this mechanism. All right. So is this clear? That there is a way to be nice. In general, I'm nice in only one direction unless I'm the super user, in which I can be nice in both directions. So good. So the kernel developers did understand human nature and behavior quite a bit. So the code that they have, so this is again, kernel code. So the kernel code that is over here it says, is it a real-time process or is it a regular process? If it's a real-time process, the actual priority value is max RT prio minus 1, where max RT prio is 100. All right. So 100 minus 1 is 99 minus the real-time priority, which basically means if its real-time priority is 99, this number becomes 0. And if the real-time priority is 0, this number becomes 99. So basically what happens is that in the case of prio, lower the better. Is that clear? Lower the better. Fair enough? So I was able to invert the sense. If it's a user process, I call nice to prio, which just adds 120 plus the nice value. All right. So what I do is I basically say that this is the nice value and I add that to 120, that is my priority. So in user also lower the better, in real time lower the better. So I can kind of transform this into some sort of a graph which just looks like this, lower the better. That is precisely what I have done. I have inverted this, so it now looks like this, which means I have made it monotonic. Right? So this is the kernel code that kind of corrects this small historical artifact and essentially says lower is the prio variable, value of the prio variable, higher is the actual priority, and vice versa. And the nice logic is nicely folded in here. So what the scheduler does is that it clearly is a differentiating scheduler, right? That if you have a higher priority, higher actual priority, which means lower prio, it will give you more CPU time, right? It will give you preferential access to resources. Essentially, you're like a business class customer, right? And if you're then, let's say different classes, first class, business class, premium economy, economy, so you get differentiated services. The same is here with different priorities, you get differentiated services. So the effect of this is that we created a monotonicity, and given the fact that the monotonicity was created, the internal logic of the kernel becomes very simple, which clearly means lower the value of the prio, higher is your actual priority. If it's 0, you are like a first class customer, and if it is 139, well, you are like the economy class customer who was bumped from his flight. So then there is some other information, metadata information, that is of value, especially when looking at statistics and also seeing, should I schedule this task or not? So there's a shared info class, so which looks at the number of times that this task has been run on this CPU. So this is a useful variable. The point is that if something has been running on the CPU, let's say for long or a lot of times, given a choice, you would like the program to again run on the same CPU because its caches are warm, right? The TLB may be warm. Warm means it will have the data. You should give preference. The time spent waiting in the run queue. right? So the point here is that if you have been waiting for long, you should get some preference, right? That is what fairness suggests. Then there are a bunch of timestamps, and then like when did we last run on a CPU, right? On this CPU, let's say you have been running on this, but the last time you ran on the CPU was a long time ago. Most likely your data will not be here. It will not be there. That is one more thing you need to keep in mind. When were you last queued to run, right? You were running, that's all right. But maybe you were running, you were waiting for something, and then, there was a long wait time. When were you actually queued, in the sense added to the run queue? So these are all interesting statistics that kind of give you the past history of a program, right? Because now, we have done a context switch. We have assigned a priority to our threads, including kernel threads. My kernel threads is running, user thread is running, a lot of threads are running. To decide what to schedule, at least you have to collect the information such that chapter 5 can schedule it. Essentially, we are at chapter 3, where we want to collect all the information that should be made available to a scheduler. So as a scheduler, whatever it wants, it can use and take an appropriate decision. So all of this information is kept here, part of the task struct. That's why I said task struct is a huge structure, which is why a pointer to it has to be saved. So now we have finished an interesting juncture where we have actually looked at some of the core mechanisms of the process related aspects of the task struct. We will look at more, so things don't end here. We'll look at more in terms of PIDs and so on. But now we'll make kind of a detour into the memory related aspects. Then again come back to the process related aspects here, right? So this is like a memory detour. So previously we were again in the process. So this was the first part, was basically on how you run the processes and kind of orchestrate setting up their state and so on. We'll talk about memory, and then we'll talk about a collection of processes. So this was more like a single process thing. So but then we will talk about multiple processes. So it's a good idea to stop this lecture here and start the next lecture from memory.